So, hi everyone, I am Sig. This is Type Systems for Alchemy, and I'm going to teach you multiple things about chemistry. Okay, so the format of this talk is a quick overview of programming languages that are used within chemistry research, and then sort of like an impromptu language design session to try and make a better one. Because the languages that are used within chemistry, at least the ones I've run across in my research for this, are not particularly ergonomic or human-friendly in any sense. Okay, so languages in chemistry have a number of different roles they fill. So one of the most commonly used languages that people who do like research chemistry interact with is this language called SMILES, which is a line, like one-dimensional representation of the structure of a molecule. So, oh, that's not quite correct. It looks like this machine is not rendering images, which is sort of a problem. Hold on. Oh yeah, they're just gone. That's unfortunate. Okay.
So you had SSH a moment ago. So you did SCP. You use Hex 11? No, it's a Mac. Oh.
Yeah. So the image assets are bundled within this blend file, so I'm not entirely sure what's happening here. I'll just try and explain over it, but it probably won't make any sense for SMILES at least. So the idea behind SMILES is you have a single string and you want to represent either an entire molecule or like the fuzzy idea of a molecule. So something that has like an open space that you're trying to search for within a database of different molecules. So the simplest sort of like example case for this is carbon-carbon oxygen. This is the SMILES representation of ethanol, which is a very popular molecule. SMILES assumes that everything that happens in a sequence is a chain of single bonds, and that all free valences are filled by hydrogen around it. So it's just sort of assumed that there is hydrogen everywhere. This is a slightly more complex example of SMILES. This is sort of interesting because SMILES is probably the best way to describe it is an accidentally Turing-complete language. There's when you represent a molecule is not a line. A molecule is, in fact, a very cyclic structure. It's not tree-like at all, either. So to represent a molecule in a single line format, you need to expose a variable and then bind a particular atom to that variable and then reference that variable later. So what's happening here is that this gets sort of implicitly done. So this is carbon, oxygen, and then this, these lowercase c's are part of a benzene ring. It's a ring of carbon atoms that are bonded together. And since that's a cycle, and you can't express that in a line, you have to do something tricky. And what happens here is SMILES requires you to pick a single path through that cycle. So in this case, there's a dominant path that is the c's that are not within the parentheses. And those are just a line. So if you want to make a cycle, you have to close the hole that you expose by just representing them as a line. The parentheses allow you to specify there's a branch called C1. That's what the variable gets bound to. And then the interpreter sort of decides that you have a branch and it should be closed again, because you probably didn't want to just branch and put a carbon out in the middle of nowhere within this ring. Also, the hash is a double bond. Or, yes. This was a more complicated that actually showed the path system. So I'm going to skip to the next part, which is charm, which is a language that is used within crystallography. So doing simulations of like building a crystal and then applying some operation onto it, because you don't necessarily want to grow a synthetic crystal every time you want to explore some property of one. This is a language that is not super popular, but is used very heavily in Harvard. It looks like this. So the bang is the comment, and it has a selection system of its own. Most systems just use smiles for their like selectors. It's sort of like the CSS of chemistry. This one has its own, which is a little unusual. So Selly is the operator for a selection. At one time, this language only allowed 4-letter keywords or variables. It now does not, but legacy never changes. There are infix operators. Okay, so there's some tricky stuff going on here. So this is a language that introduces a set of expression context, puts them in a stack within a PHP compiler, and and expects all programmers to know exactly what context they're in when they're typing anything. There are no type errors that come out of this compiler. So if I move that .n dot, which is an infix Boolean operator, to like between Selly and Atom, it would just sort of like blow up. It might consume all of the memory on your system. It's not particularly user-friendly. So things Charm has. It has control flow structures. This one's intentionally Turing complete. It has only go to and single branch if though. So you have a conditional instruction and you have a jump instruction, but that's all you get. It has an actually interestingly like easy way to express like calculus operations like integration and differentiation on functions that are expressed in terms of like molecule positions or atom positions. It does not have arithmetic. So you can do differentiation on a function, but you cannot subtract 2 integers. It does not have actual variables. If you want to assign something to a variable, like a file handle, like the molecules you're reading to do your simulation in, or the file handle you're saving to, you refer to them only by integers. It does not have blocks either. Like I mentioned before, it's an entirely stack expression-based compiler. And there's no scope, and there's no way to tell what part of a expression you're actually in. This is what an actual like practical example of this looks like, I suppose. So this is code that selects within one particular molecule the nitrogen atoms, the whatever Ca is, I'm drawing a blank right now, and carbon, and tries to apply a force to hold them in one place. How do you apply a force to hold something in one place? You cons harm it, of course. The absolute just specifies all of these things, all of the expressions are parsed as arguments to a function that is the first one. The implementation of the function is expected to handle all possible cases of all possible contexts it could introduce. Cons, harm, and absolute are arguments, and then Selly is an expression after that the cons function has to handle. Okay, this is what actual code that you'll see in research looks like in Charm. I don't know what any of this does. It's very, very hard to understand. So the dash is, it like escapes the new line that comes after, even if a new line doesn't come after it, like in the case of these comments. Open unit is the file handle command, and you bind all those to variables that are then referenced in this lower section that does something. It applies like heat and pressure to whatever is in the file, I guess. It's incredibly hard to like infer that. Okay. So Charm is a good language for crystallography. It's a little awkward though, because its compiler is non-performant and its runtime is non-performant. If you want to do anything on a large scale, you're going to end up spending a couple days just doing the simulation. So most people don't use that particular sort of language. A lot of people within crystallography and some sorts of research chemistry use this language called Gaussian 09, which despite being named Gaussian 09, was actually introduced in 1972. Okay, so this is a picture of diphenyl, I think. It's two like rings of carbon, aromatic rings, that are bonded together with another carbon between them. It's a fairly simple structure. In SMILES, it would be like a 16-character molecule. In CHARM, it would be 2 lines of selectors. In Gaussian, it's it's this. So the only way you can express anything in Gaussian is by dumping a table of floating point values. The left side indicates what atom it is. The fragment doesn't indicate anything, really. It's just there. It's necessary for performance optimization within the simulation. And then after that, you have what is, depending on how this particular expression is being parsed and like what order you've loaded your files, this is either positions or the charge of each particular atom. And the step at the top is actually just nonsense. It doesn't do anything. I need to move my camera. If I can find it. I have run out of floating point values. Where is everything? Where did it go? Oh. Is that? Not quite. There we go. Sorry, I make my presentations in Blender. It's a little weird. Okay. Skip through this. Okay, so things Gaussian 09 has, and it looks like I'm a little bit off in the camera position. It has decent floating point value handling. It's really important to the runtime. It has an actually very clever optimizer. It's the only simulation package you can get for most sort of force field equations within chemistry that will actually like narrow the state space of what you're simulating and actually make sense of what you're doing. Things Gaussian 09 does not have: name binding for anything, semantics of any sort, any concern for the needs of humans. Okay, this is what a function call looks like in Gaussian 09. Onium is an algorithm used for calculating the field potential around molecules. The rest of this is sort of nonsense, except for 6-31G, which is the namespace the function's in, and AM1, which is the name of the function. All functions are named like this. All namespaces have these, the weird sort of identifiers. These are actually citations within the documentation of Gaussian 09 that link to papers that describe the algorithm. Okay, this is what actual Gaussian 09 code looks like. So the language is modernized a bit from what I've described. You're now able to use letter characters within some descriptions of what molecules are. They have to be bound to constants somewhere else. They can only be floating point values. They also won't necessarily compile all the time, so you might have to run your job again. So this is test code from the compiler. Okay. Do I have anything else? No, I don't. So these languages are terrible. I would never recommend doing any work with those. I would never want to use those in chemistry work that I was doing. So what I had planned for the rest of this talk, which is not very long now, was to sort of walk through and talk about design aspects that could make these things better. So I'm just going to like talk over that, I guess, instead of like trying to put something concrete together. So this is a functional programming conference, right? What we just saw were not just imperative languages, they're barely above assembly in terms of the semantics they express. They're also the SMILES representation that I showed first. I hope that some of that went through. It is a system that expresses late binding like semantics in a very informal, like completely inconsistent and really hard to reason about way. So as a language designer, I look at these things and think, this should not be the case. This is the worst possible outcome that this industry could possibly be in when almost everybody in this field does their work with computers and these languages. So the institutional structure that has grown up around these languages is such that a professor has an idea, converts that to a specification, and a series of 6 graduate students slowly convert it into Gaussian or charm code. Or they work with like a GUI application that does a lot of this work for them. Especially in industry, you only see GUIs that are either attached to Microsoft Excel or just completely self-contained corporate products that hardly anybody knows how they work. So this is like a really bad situation to be in. How could we do this better? So this is in particular a field that I think could be seriously improved by an open source functional language coming into it. So the smiles-like representation of molecules is a really interesting case because it would be so much more, not necessarily efficient, but easier to reason about, something that's simpler in the cognitive sense, to just have a cyclic binding within maybe an ML-like language, something like Haskell. I like Haskell. And the other cases, the languages that express simulations, are probably better off being represented by a linear logic or process calculus, like encoding of the nature of chemical interactions and the simulations over them. So all of these systems I showed you, they're imperative in the sense that they were originally written for mainframes, and they spit out a file called tape. You take your tape file, plug it back into another operation, and you have to do this consistently. So there's a lot of sysadmin work happening within chemistry research right now. That's nonsense, right? That doesn't need to be there. What would be much cooler is to have some sort of like semantics of temporal implication. So like a linear logic like framework of this operation happens and then this operation happens if it's exceeded, on the idea of like chain and chemical operations. So growing a crystal or the like steps in synthesizing a medicine or something. And also applying a typed representation to these languages would be a really good step to go in. So these languages, and a lot of languages used within industries that don't have exposure to functional programming, don't have any sort of static analysis. They have nothing. You don't get any results out of your program until you've been running your job for 2 hours and it fails. To be able to like kill a class of errors is something that functional programming has as part of type systems or other static analysis systems. C people get some of it, of course, but it's not quite as good as having a total guarantee about the code you get. That hasn't propagated to industries anywhere. This is a mistake. As functional programming people, we should be working within other fields to get this sort of safety guarantees to other places. In chemistry, it's really important because the simulation results you get out of like doing tests on medicines is all the information that you get before running a trial on animals. Sometimes it's all the information you get before running a trial on humans. Having a type error in your code that might propagate into an undefined that gets hidden in your data might kill a number of animals or possibly some people. So I've got 1 minute warning, so I'm going to stop here and take questions if anybody's interested in this topic. Sure. Thank you.
So I also have some experience with terrible esoteric domain-specific languages.
Okay.
Don't make another one. Just do an embedded DSL in like Haskell.
That's a pretty good way to go about it. It's difficult for this particular domain because almost nobody has ML or Haskell knowledge. It's much easier to sell them a product. But having it expressed as a DSL with semantics of a host language would be a pretty good way to go about it if somebody wants to apply that technique to it. Yes?
Do you think something like Clasp would have kind of community?
Clasp, like the,
So Clasp is a common implementation I come from C++. So presumably a lot of these folks are running like C++ code and stuff like that. And this was invented by a chemistry professor for his own like use.
yeah, C++ is pretty common. It's
So-
competing with Fortran still, but yeah, a system that could build on top of the library foundations would also be a really good way to break into the space. If you could do something like applying typed guarantees to the libraries that are commonly used within chemistry, that would be a fantastic way to just like make a sweeping, large positive change to the entire industry.
Seems like even just like a little DSL that compiling down to Smiles code would be like a small project and helpful, right?
Yeah, so Smiles actually gets pretty long. One of the images I was unable to show was an example of an actually complex molecule expressed in Smiles. Smiles is a standard for representing molecules now because it's the only one you can actually practically type. That's not necessarily true when things get larger, but for smaller molecules, all the other representations are just as long as the names of the chemicals. So they're not quite that useful. But there are definitely some problems with it. It's slow to parse. There are no static guarantees about anything, of course. You can have cycles that don't make sense. So you can have cycles, you can have like a benzene ring, and then you can have another benzene ring on another axis, and then you can have another, and then just keep like packing them until you have a perfect sphere of carbon.
So that's what I like. You had like some kind of implementation
Yes.
that had those kind of semantic properties.
Yeah, having some sort of
still plug it into.
All right,
Yeah.
if we can move questions just to the hallway, you can
Okay.
ask all the questions you want, and so we can